preview exercises were chosen because today we're going to be looking at the ideas that you've already spent some time looking at and actually coming up with like all the correct answers. And we're going to formalize it a little more today and give you some definitions of words, okay? So this first idea here, number one, let me just stop for a minute. I'll pause. So as I said, we're going to be talking about a lot of these ideas today, but we're going to be formalizing these ideas with some definitions of some new vocabulary. The vocabulary will be new to some of you, and it may be a review for others. So please do not hesitate to ask if there's something today you don't understand. So the main thing I wanted to talk about with the preview exercises, we'll come back to these, is I wanted to talk about this graph right here for a minute and look at part C and D. So C says, describe the x coordinates of all the points on the graph. Well, it's impossible to look at all of the points on the graph because this graph extends to positive infinity in both directions. So what could you tell me about the x values that's allowed to be put into the equation for this graph? Even though we don't have the equation, we just have the picture. What could you tell me about the x values? It goes from negative to positive, negative infinity to positive infinity, right? In other words, there's no restrictions on the x values here. Any x value on this number line, on the x coordinate, which represents the real number line, is allowed in. So the way we represent that is it has to be a set. So anytime you represent a set, you can use set builder notation or interval. In this case, we're going to choose to use interval notation, and this represents the set of all real numbers. Ashlyn, do you mind getting that door so we're not interrupted again if someone decides to have fun in the hallway? Okay. So this is a set. It's a set of all the input, and we're going to formalize the name of this set today. We're going to be calling this the domain for this particular graph, the domain. I'm just going to give it to you now. It's a set of all inputs. Okay. We'll revisit that definition again. And then many of you described the set of all your y coordinates by doing this. Y is greater than or equal to 1. And in set notation, we represent that. Since 1 is included, we use our staple, formerly known as the bracket, with a 1. And there's no end. It goes to positive infinity. So that represents the set of all real numbers starting at 1 and growing without bound. Okay, so you did a good job on that. So we call this set, this is the set of all outputs. Okay, all outputs. We call this the range for this graph. It's the range. All right, so if I asked you for the equation for that blue graph right there, could anybody tell me what it is, the equation? Alan? Absolute value of x like this? Yes. Then plus 1, okay? And that's correct. And if you think about the two lines you drew above, right here, you drew the line y equals 2x. And when you draw y equals 2x, it looks something like this. Oops. Gotta erase that point. -2, -4, -3. So here's the line y equals 2x. Oops, I didn't do a very good job. I must have missed something there. No, it's just the scale's kind of funky here, huh? Did I miss anything? Why does it look so weird? Oh, it's not 2, 2, it's 2, 4, 2, 4, and 3, 6. Okay. I knew something had to be wrong because it was a straight line. Done. Just give me my little eraser. Okay. All right, so there we go. This should look better now. Kind of. All right, so there's y equals 2x, not a very good job. And then we saw that the graph for y equals 2x plus 4, we didn't really have to do, so let's call this y1. y2 was all of the output values for this first one, and then you added 4 to them. So all you have to do is literally walk up 4 steps, right, from every single one of these values to get your new points. Just walk up 4 steps from -1 to 3, and -4 to 2, and -6 to -2. And that would give you your new line, if I drew it correctly. Same is going on here. If we put in the absolute value function, the absolute value function looks like this, because we know all the output has to be positive when we come out of our absolute value function. So our range for the absolute value function is 0. So this is y2 is the absolute value function. So the range here would be 0 to positive infinity. And the domain is the same. The domain is all real numbers. And what Alan noticed is that it's not the purple function, it's not the absolute value because you don't start at 0 for your output. But he noticed that every single one of the outputs just took a step up the y-axis, 1 step. So you just add 1 to all the original outputs. We're going to talk about this later on when we're going to spend 3 days doing a topic called transformations. So that's where this is heading. That will be about a week or 2. Okay. All right, so let's take a look at today's material. The first thing we're going to do here is we're going to define what the mathematical definition is for this term called relation. So you want to start us off, Clay? Yeah, please. So it says here that, we can represent any sets of data with this ordered pair x and y. Does it always have to be x and y? No. Right, it depends on what variables we're looking at and labeling our axes, okay? But we traditionally call it x and y. And then when we have a specific story that, say, might involve time, height versus time, then we would change the values of x and y, the letters, to represent the height and the time. So if we were looking at a story about the height of something versus time, this might be what the ordered pair looks like. Okay. So the example that we're going to look at for a little bit today involves, when I wrote this problem, I was looking at the Boston Celtics team roster, and I don't think, does anybody follow the Boston Celtics? No? No? All right. I don't know if any of these guys are still on the Celtics right now. They've traded so many people. I know they've traded Jeff Green. So here we have 4 Boston Celtics that were on the roster at the beginning of the 2013 basketball season. And these are their respective heights, 6'9", 6'2", 6'5", and 6'9". So I can create a relation here. A relation is just a set of ordered pairs. So look, how do I know I'm creating a relation? Well, here's a set, because I see these braces that indicates the set. And here are 5 or 4 ordered pairs. Okay. And I've chosen to put the input as the name of the Boston Celtic, and the output is their height. So this is what we call a relation. Nothing fancy, just a set of ordered pairs. Okay. Now, this is where the idea of domain and range comes in. We just looked at the idea of domain and range with a graph, but it doesn't have to be a mathematical graph. It can just be a set of ordered pairs like this, where the first input into the ordered pair, what you typically call x, but since we're not doing any mathematical manipulation with this, like multiplying it or squaring it, it's just the Celtics name. So the input, the set of all inputs, is Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace. Since they're the first input into each one of these ordered pairs, we call that the domain of the function. And I want to point out a word that people often forget about when they're talking about the domain, and that's this word right here. Anytime you talk about a domain or a range, it's always going to be a set of numbers, always. So you're always describing a set. A set of numbers, or in this case, a set of inputs, which represents these four names of the Boston Celtics. Now the set of heights, which is the outputs here in these ordered pairs, are the second components, is called the range of the relation. And again, it is a set. Okay, both of these are sets. And notice you see the braces there as well to indicate that it's a set. So that's one of the important things when we talk about domain and range is whenever you represent it, whether you say it, write it verbally, you have to always have the word set of real numbers, or parenthesis, negative infinity, comma, infinity, parenthesis, if that's how you're trying to represent the set of all real numbers. Visually, one way we can do it is we can have these sort of ovals represent the set of all your inputs. The domain is the set of all inputs. And the range is the set of all outputs. Okay. So I want to ask the same question that I asked in the very first preview exercise. Does each input in this domain, does each input correspond to one and only one output? So let me write that down. Does each input correspond to one and only one output? So I hear a no. Do I hear a yes? No yeses? Okay, so I'm going to take each person's name and ask you how many heights does that person have. Here's Avery. Avery's an input. Does Avery go to one and only one output? His height, 6 feet 2 inches. So the first person passes that question, right? Okay. Here's Jeff Green. Does Jeff Green go to one and only one output? Yes. So Jeff Green passes that. Here's Keith Bogans. Does Keith Bogans go to one and only one height? Yes. Then here's Gerald. Does Gerald go to one and only one height? Yes. It didn't say that two players couldn't have the same height. It just says, does each input correspond to one and only one output? What's your answer? Yes. All right. So now we're going to reverse the order because there's nothing telling me that one of those members of the ordered pair has to be in the input and one has to be in the output. It's not an equation where one value depends on another. So I'm going to switch their names and heights around. So what's the domain going to look like here? If I put the domain now, it's going to be the set of what? Heights. The domain is the set of heights. So let's actually write those set of heights in, the domain. So someone want to tell me how to fill in the domain, what I would write? Okay, go ahead, Amber.
So 6 foot 9 inches.
Yeah, with a little dot, right?
Yeah.
Okay.
6 foot 2 inches.
6 foot 2 inches. Yep, with a little dot.
6 foot 5 inches.
Yeah. And do I have to do 6'9" again? No, because it's already there. Okay, 6'9". All right. So there's my domain. It's the set of the heights. And if I have duplicates, I only write it once. Just like when we were talking about the Beatles reunion, right? Way back in class number 2. When you do the intersection of two sets, you only represent an element once. Okay. So what would the range be here? The range would be the set of what? The set of players' names, right? So we've got, I'm just going to use the first name, Jeff, and we've got Avery, Keith, and Gerald, right? All right. And okay, 6'9". Where does 6'9" go? To Jeff. Oh, and Gerald. All right, well, that's a little different from the first picture we looked at. 6'2" goes to Avery, and 6'5" goes to Keith. All right, so without reading, if you can not look further down on your page, if I told you that we're going to give the most valuable player award to the person who was 6 feet 9 inches, who would I give it to? No, we can't give it to two people. We can't give it to Jeff Green and Gerald Wallace. Is it clearly defined which person gets this most valuable player? No, because for each of my inputs, do I have exactly one and one output? No, because for 6'9", 6'9" goes to two different people. 6 foot 9 inches goes to Jeff, and it goes to Gerald. And this is okay based on the definition of what a relation is. It's just an ordered pair. So this is okay as a relation, but it doesn't satisfy the idea that for each input there corresponds one and only one output. So for that kind of relation, where we have one and only one output, we've got to give it a new name. And the new name for that type of relation is called a function. And this is the major concept that we're going to work on for the rest of this class, including whatever class you go to after this or classes you go to after this. Functions is a major concept in any math class starting now for the rest of the time you study math. So I've written a function in two ways, and on my paper I've underlined that. On yours it's not underlined. You may want to put stars or whatever beside it, highlight it when you get home, or if you have a highlighter now. But a function is a relation, but it's a special relation. Everything's a relation, because remember, a relation, you don't have to have any special talents. You're just an ordered pair. But to be a function, you have to be talented. To be a function, you have to have one output value, just one, for any input. Said another way, if we use this idea of domain and range, for every element in your domain, you have corresponding one element, exactly one element in your range. So when we had the names first and the heights second, that would be called a function. When we turned it around and had the heights first and then the names, we got into trouble. Because if we looked at 6 feet 9 inches, we had no idea which person we were talking about. So that's not a function, but it's a relation. It's kind of like the idea that all squares are rectangles, but not all rectangles are squares, right? Squares are a subset of rectangles. Functions would be a subset of relations. So I've kind of given I've let the cat out of the bag here because I've already answered 7. Which one of these sets of ordered pairs represents a function? P or H? P, right? It's the first one. We sort of already talked about that. I forgot I had written that as a question. All right. So one of the new things we're going to need to do is to talk about function notation. And we're used to seeing X's and Y's. And we're going to start looking at what kind of new notation now do we have when we want to talk about functions. So here's a table. One of the ways to represent a function is with this set of values that's in tabular form. Another way was looking at graphs, like we looked at the preview exercises, the absolute value of x plus 1, or 2x, y equals 2x. So we could have a graphical representation. We could have a table like this. Okay, we can have just an equation, an algebra representation. And sometimes we can just describe a function with words. I could say, yeah, all the heights of the people on the Celtics team is 6 inches more than all the people on the high school varsity team at Mohawk. I could just describe it in words, something like that. Okay, so here we have some terminology and some names, and some of this is going to be new to you, and some of you, this is old hat. But when we talk about a function, we use these letters, little f, little g, little h, big F, big G, big H. We can use any letter, but these are typically the letters. We stay away from X's and Y's because we use X's and Y's to talk about inputs and outputs, typically in an ordered pair, okay? But I could use big P if I wanted. I could use big S or little p and little s, okay? But these are sort of like the generic names for functions. When we use functional notation, Y, which is typically your output in your ordered pair, is now going to be the same thing as f of x. And notice how I just read that. F of x. It doesn't mean f is being multiplied by x, which you learned when you first started algebra, because you learn that when you have parentheses between two letters, it means multiplication, but not when we talk about functions. So f of x means the same as what you've been calling y. So now when you write your ordered pair, you're traditionally going to write it now like this. Instead of x comma y, you're going to say x comma f of x. To really reinforce the idea that this output value, f of x, is dependent. It's a function of this input value called x. So every time you see this notation, regardless of whether you're working with x's and y's or t and h's, whatever is in the parentheses of your function notation is the input value. Or it could be an expression like x plus 2 or x plus h, or it could be simply a number like 2. It's any input, either a value or an expression. When you evaluate your function at that input, out pops your output. So in this particular example, my input is the time measured in seconds. When I put that input into my function, in this case, I get the output, which is the height of the baseball in feet. So it just takes a little practice now because you're so used to writing x and y or y equals. Now you say f of x or g of x or whatever your input variable is goes inside the parentheses. Any questions on that in terms of the notation? Okay, well, let's practice a little bit on how to interpret this notation. So here we have our table, and here we have some expressions. And so I'm asking you to look at this table and tell me, what does this mean? The way I read this, it says, what is the value f of 2? What is the value for f of 2? That's how we would read it, f of 2. So you say 2 is my input, which means I'm looking for 2 seconds in my table. So you go up to your table and you look at the bottom row and you find 2 seconds and you put a little like bingo chip right there. There you go. There's my bingo chip. And then to find the value of your function, the output value gives you your height. At 2 seconds, you put a bingo chip on 99. And that represents the same thing. The number 99 represents the same thing as f of 2. Okay, so the output 99 is the height of the baseball in feet. Okay. So these two things have an equal sign between them. They mean exactly the same thing. Okay, f of 2 means exactly the same thing as the number 99. So my input is 2. I found my output 99. And now I ask you to interpret what this means, f of 2 equals 99. Since you're starting with the input, start your sentence there. At 2 seconds, right, my baseball is 99 feet high. Boom. Very simple. Any questions on that at all? Okay, what about f of 0? Can someone help me put my bingo chips? Where would my yellow bingo chip go for f of 0? Someone other than Amber, who's giving you all the answers? I just want to know where 0 is. Which 0 do I look for? Time, right? Because that's my input, right? So where do I put my 0 bingo chip, Nick? on the 0 right here in my lower row, right, my bottom row. And then you actually gave me an output, 3, right. So before I even start measuring the height, my initial time here is t equals 0. It's just when I take my first measurement with whatever instrument I'm using, the height of my baseball is 3 feet above the ground. So you would write that as 0, f of 0, and then you could be more specific and say 0, comma 3. So again, this is 0 seconds, comma 3 feet. So if I interpreted this, someone want to give me an interpretation of this equation right here? Yeah, Ashlyn? At 0 seconds, the height of the baseball is 3 feet. Yep, perfect. So just, oh, Amber? The height of my baseball started out at 3 feet. Starting out at 0 seconds all mean the same thing. And actually, especially when you deal with physical applications like throwing things up in the air and talking about heights at certain time, whenever you have t equals 0, there's a special word that you'll see a lot, whether you're looking at books or in applications. When t equals 0, they'll often use this word, the initial height of my baseball was 3 feet. So when I ask you to interpret stuff, I'm always looking to see both of the numbers here, both the 0 and the 3, along with the units. However, in this case, where t equals 0, the minute you use initial, when you use that word, I know that my input value is 0. I know that immediately when I see that word. So if saying at 0 seconds feels a little awkward to you, you can say initial. You could say initially the height of the baseball was 3 feet, or the initial height was 3 feet. It all means the same thing, whatever you feel the most comfortable with. Or as Amber says, at the start, it was, how did you say it, Amber? To start with, right. So this to start with is the same thing as t equals 0 seconds is the same thing as the word initial. Okay, all of those is fine. Okay, so how does this next one change? What poker chip do I know? The green poker chip or the yellow poker chip? The green one, because I know my output is 103. So now I've got to go up to my table and put my green poker chip at 103 and work backwards. Now I'm asking, at what time was my baseball 103 feet above the ground? So now I'm solving this equation for x. So what is my answer here? X equals what? 2.5, right. My poker chip or my bingo chip's at 2.5. So now I'm saying the baseball, I'm starting with 103 feet. I'm starting with my output. So the baseball is at 103 feet after 2.5 seconds. So see how I've sort of my phrases in my sentence changed? I was given my output, so that was sort of the first part of my sentence. I start with my output. The baseball is 103 feet high. I found when it was 103 feet high at 3 seconds, so that was my ending. So that's functional notation. That's how you would interpret it. Again, I want to point out, because some of you missed this on your project, when I ask you to interpret or explain what an ordered pair looks like, you have 2 numbers and 2 units. So notice the ordered pair that would go with this is 2.5, comma 103. So in my sentence, I need to see the actual number 103, and I need to see the actual number 2.5, and I need to see their corresponding second units, in this case, feet and seconds. Okay, so that's just a good practice to get into when you're trying to interpret the meaning. All right, so now you have your class activities. You've got quite a few. I'm sure you'll be busy right to the end of class. Any questions, please use your flags. If you're working alone and you want to be able to talk with someone, feel free to change tables. Okay? So